Hello and welcome to this FMSP online revision recording for the OCR specification module M2 Mechanics, and this topic is energy, work and power. Under that heading in the specification there are 5 points. The first one is about understanding work done by a force. Well, I'm sure you remember that's force times distance. But there's a reminder here that it's not always so when the displacement isn't parallel to the force itself, and a little bit of trigonometry is needed in here. Secondly, energy, gravitational potential energy and kinetic energy. I'm sure you remember mgh for gravitational potential energy and half mv squared for kinetic energy. The third point is about the relationship between energy changes and the principle of conservation of energy that says that energy is not lost from a system, only converted from one kind to another. And we have to remember the part that work done does as well. Fourth point is the definition of power, which is the rate of doing work. And typically we find ourselves using the relationship between power, force and velocity. P is Fv, or swapping it around, P divided by V is F. And then point 5, using these things to solve problems. For example, the instantaneous acceleration of a car. And in case you're not sure what that means, it doesn't mean accelerating from 0 to 60 in an instant. It means the acceleration at a particular instant, and we'll see an example of a question using that phrase in a moment. So here are some key points to remind you about. And the first one, or the first 4 I should say, are quite important because you don't get these in the formula book, so you better memorize these 4 expressions. A comment about gravitational potential energy. It's relative to a zero level. Usually that's obvious, it's ground level or the lowest level in the motion, but you can define that. And then a comment about this expression, because as I said before, you only need this part of the term if the force being applied is at a different angle to the displacement, and we'll see an example of that in one of the questions I've chosen. Now then, connections between energies. And here's a 4-term energy equation. If there's no work being done, then potential energy plus kinetic energy before equals potential energy plus kinetic energy afterwards. But you normally choose your zero level so that one or other of these two is 0 anyway. And then if there's slightly more going on, if there's work done in or out of the system, you might need this longer equation, and one of the questions I've chosen involves this equation. So let's get on with the exam questions then. And can I just remind you that at any point, if you want to, you can pause the recording or go back and read the question again at your leisure if I go too quickly. Afraid I'm not very good at drawing vehicles, but here is a vehicle. This is the car of 700 kilograms. It's therefore got a weight of 700 g-newtons and a corresponding resistance force stopping it sinking through the road. But all the forces we need to consider are the horizontal ones. A driving force which for convenience I'll show out to the right. It's not really coming out of the windscreen, but we imagine that force acting forwards, and then what we're told is a constant resistance to motion of 400 newtons. And what I'm doing is trying to get all the information into the picture. So what else is there? At an instant when the car is travelling at 12 meters per second, its acceleration is 0.5 meters per second squared. Okay, that's got all the information. What do I need to do? First two parts of the question, find the driving force, so that's find F, and secondly, find the power at this instant, in other words, the instant when the speed is 12 meters per second and the acceleration is 0.5. Let's do that and then come back for the rest of the question. So first of all, the driving force, and we're going to use F equals ma, and I've used F on my diagram to mean the driving force. Don't forget that F here means the resultant force. So that's all the components of the force, the driving force forwards minus the 400 newtons resisting motion, and that's equal to the mass, which was 700, times the acceleration, which we're told is 0.5. So that looks quite simple to solve. Half of 700 is 350, and that's F minus 400. So if I add 400 to both sides, my driving force is 750 newtons. That's that nailed. The second part, what about the power? So I'm going to use power equals force times velocity. And we've found the force, it's 750 newtons. And I need to multiply that. Not quite sure why I wrote the newtons there, I'm just going to remove those for a moment and pop units back in at the end. Multiply that by the velocity, which is 12 meters per second. 750 times 12 is 9,000. And the units for power are watts, although I looked at that and thought I'll give that as 9 kilowatts. But either of those two answers is acceptable. Well, that's the first two parts dealt with. Let me just say that there's a mark for the method and a mark for the answer in each case. Now let's look back at part 3 of the question. We're now told the maximum steady speed of the car on a horizontal road is 35 meters per second. Steady speed. I paused over that because if it's steady speed, that must mean the acceleration is 0. Constant speed it really means, doesn't it? And then the question is, find the maximum power of the car. Well, when it's giving its maximum power output, we're getting the maximum speed, and that's the important link here. So then, let's just write that down so the examiner can find it. Maximum speed implies and is implied by maximum power output. And the fact it's maximum speed also tells us that the acceleration equals 0. Well, looking at my diagram again, if the acceleration is 0, then the force to the right must equal the force to the left. So that gives me F equals 400. So what about P? And I'm going to call it P max here. P equals F times V. It's 400 times that speed of 35 meters per second. 400 times 35 is 14,000. And that gives me a maximum value of either 14,000 or 14 kilowatts. And once again, there was a mark for method and a mark for answer. And that's 6 marks so far. Let's read the last part of the question. So, having dealt with those issues, something's going to change. We're now going to drive up a slope of a constant angle theta. The maximum steady speed, now we know what that means, acceleration is 0. The maximum steady speed up the slope is 12 meters per second. And if it's the maximum, then the vehicle must be using the maximum power. So remember, we want to use maximum power and acceleration equals 0. And I think I better draw a new diagram. And even though it said it didn't tell you what theta was, don't take theta as too small when you draw a diagram. You want to be able to see what's going on. So here's my angle theta, and my vehicle now heading up the slope, and I'm just going to put in the forces along the slope first. The 400 newtons constant resistance force hasn't changed. The driving force is parallel to the slope, and we have a reaction force, but of course the weight is vertical, so we're going to have to do some effort overcoming the component of the weight force that's down the plane, or parallel to the plane. So if I split the weight into components, the angle theta is in there, there's a component of 700g sine theta down here. Now I'm just going to note that the acceleration is 0 because we're told it's the maximum steady speed, and that speed is 12 meters per second. And I've got my connection that F is P over V, and remember I've already found what the maximum power is. P max is 14,000 watts. Okay, so since the acceleration equals 0, the forces up the plane equal the forces down the plane. So F must equal the 400 resistance plus the 700g sine theta. And now I'm going to use the fact that F is P over V, and it's my maximum power divided by 12, which is the velocity, and that's equal to 400 plus 700g sine theta. Before I go too far, in fact, I think I'm going to divide every term by 100 to make it a bit easier for myself. Well, this left-hand fraction doesn't come out as very simple because of the multiple of 3 on the bottom. So I'm going to write 35 over 3, which is what 140 over 12 is equal to, but I'd rather not deal with recurring decimals at this stage. So I'll write out the equation and then multiply through by 3. Of course, if you're adept with dealing with decimals, I'm sure you could calculate this another way and get just as good an answer. But this is the method that suits me. Well, if I take 12 from both sides, I'm on the way to isolating theta. Let's divide both sides by 21g, and that's equal to sine of theta. Okay, I'm running out of room, so let's move over here. So theta equals sine to the minus 1 of 23 over 21g. And using g as 9.8, of course, that gave me an angle, not a very big one, of 6.4167 ... Therefore, I gave that as 6.42 degrees to 3 significant figures. I normally give angles to 1 decimal place, but in this case, because that meant it would only be 2 significant figures, I've put the angle to 3 significant figures. So, where were the marks for this? 1 is for using F equals PV, which came into play here. That's 1 mark. The next mark is for having a 3-term energy equation here, and getting the 3 terms correct is worth an answer mark. And the final mark of the 4 is here for having the correct answer. So there we go, that's the first question. Let's look at another one. A block of mass 25 kilograms is dragged 30 meters up a slope inclined at 5 degrees to the horizontal. It's pulled up by a rope. inclined at 20 degrees to the slope. So the force being applied is not parallel to the distance that the block moves. The tension in the rope we're given is 100 newtons, and the resistance to motion. I'm going to have to get this all on a diagram, and remember, very important with all mechanics questions, draw a nice clear diagram with everything on it. Well, it may only be 5 degrees, but I've exaggerated the angle so that I can see everything that's going on. And the block starts, I'll mark it lower down the plane here, it's 25 kilograms. And it's going to be pulled up the plane by a tension that's at a different angle to the plane. So there we go. There's my tension, and we're told that that's 100 newtons, and the angle in here is 20 degrees. Well, the block is pulled up to a new position, and in doing so it moves 30 meters. For convenience, I'm going to call this position A and the higher position B, and also just going to tell you straight away that I'm going to use the lower position as the 0 level for gravitational potential energy. The other thing is, it's being pulled by a force all this time, and forces don't just move, they accelerate things, so it's being accelerated. And when it's in the new position up here, it's going at a speed v. And I've got to find v later on in the question. It was at rest to start with. Okay, now I'm just looking to see if I've got everything written on the diagram. Just mention, of course, there's a weight force here of 24 g newtons, reaction force, and yes, there's the resistance to motion of the block. Okay, so I've got 70 newtons there. Now I'm going to need to consider a component of this force. So I'm just going to split the tension into two components, one up the plane and one perpendicular to the plane, and the crucial one is the one parallel to the plane, which is, if I can write it in there, 100 cos 20, because it's next to the angle. Another thing that's going to be important is how much this block has risen, because I'm asked about the change in the potential energy of the block. And this height here, once again, the angle here is also 5 degrees, so the rise in height is 30 sine 5 degrees. And my 5 degrees there seems to have acquired an extra 0. That's 5 degrees. Okay, with all that in mind, let's look at the question. First of all, the work done by the tension in the rope. Well, work done is force times distance, but bear in mind that the magnitude of the force wasn't all acting in the same direction as the displacement. So the work done is force times distance, but in this particular case the component of the force up the plane was 100 cos 20, and the distance was 30 meters. Well, if you multiply all that out, you get 2820 joules to 3 significant figures. But I'll just make a comment that although we have an answer there to 3 significant figures, later on I'm going to use the more exact value, which I'm just going to pop back in here, of 3000 cos 20 degrees. Okay, that's the work done. Second part of the question asks, what is the change in the potential energy of the block? Okay, well, change in potential energy if I was doing this completely blind, I'd just say change in gravitational potential energy equals the GPE after minus the GPE before. Now, after is when it's in position B, and before is when it's in position A. And of course, we chose the 0 level to be when it was at position A. So we've got mgh at position B. Mass is 25, g is 9.8, and as you remember, we wrote on the diagram that the height it's risen is 30 sine 5 degrees. And that's minus 0 because the original GPE was 0. Well, calculating all of that, I'm going to write down it's 7350 sine 5, because that's exact, and as a numerical value 641 joules to 3 significant figures. But again, I'm going to come back to the exact value for the last part of the question. Okay, lastly then, the speed of the block after it has moved 30 meters up the slope. Well, this is going to be an important energy calculation. So let's look at all the components of the energy. And I'm going to write out my full 6-term energy equation. That the GPE in the original position plus the kinetic energy in the original position plus any work done into the system is equal to the GPE afterwards plus the kinetic energy afterwards plus any work done out of the system. And I always write the equation in this form because everything's got a plus sign. Don't get confused about the negatives. However, the original gravitational potential energy we took as being the 0 level, and the block started before being lugged up the plane by the cable. It started at rest, but we did do some work done. So that was the work done by the tension. It's above there, and we had 2,820. Now I just want to remind myself it's actually 3,000 cos 20 degrees. And then gravitational potential energy afterwards, well, that's over here to the right, 7,350 sine 5 degrees, plus the kinetic energy when it's in its new position. Well, that's what we don't know. It's half times the mass, which is 25, times the speed, which we're asked to find. So there we go, v squared. But there is some work done out of the system, because there's this constant resistance force of 70 newtons. So that's applied all the time it's been moving up 30 meters. So there's a force of 70 times a distance of 30 meters, which is work done out of the system. Well, let's deal with all of that then. So moving everything to the left, I have 3,000 cos 20 minus 7,350 sine 5 minus 70 times 20, which is 2,100. And that's equal to half of 25 times v squared, which is 12.5 v squared. Well, I calculated everything on the left and then divided by 12.5, and that gave me an answer for v, which was 2.51 meters per second to 3 significant figures. And I just want to mention about accuracy and not always using 3 significant figure rounded versions for later parts of the question, because the answer I had here in its most exact form before rounding was 2.50572, etc., etc., which I rounded up to 2.51. If you'd used the various numbers that appear here, already rounded to three significant figures, you'd have had a reasonably different answer. 2.51396. Well, that's almost in danger of being rounded up to 2.52. So let me just say, keep the full accuracy in your calculations right until the end. Well, I hope that was a useful reminder about work, energy and power. Don't forget, you can look at all the other topics in M2 on the other online revision recordings.